Hello, we're here to discuss the measurement of an equilibrium constant lab. This lab involves the reaction of iron 3 plus ions reacting with thiocyanate anions and producing the product iron thiocyanate. Iron thiocyanate is a pretty neat product because depending on the concentration of this product, you will either have a yellowish color at low concentrations or a darker reddish brown color at high concentrations. Now what we want to do is relate the concentration of the iron thiocyanate to the concentrations of the iron 3 plus and the thiocyanate ion at equilibrium. If we can do that, we can actually calculate the KEQ, or the equilibrium constant, for this reaction. Now remember, the equilibrium constant will either be a number that is less than 1, 1, or greater than 1. And those values indicate to what direction the reaction lies. So let's talk about how we're going to calculate the concentration of iron thiocyanate, and then we'll see how we can get the concentrations for the iron 3 plus and the SCN minus after that. Okay, so in this experiment, the first step that you're going to do is try and determine the concentration of iron thiocyanate at equilibrium. Now, the way that you're going to do this is actually pretty tricky. What we're going to do is we're going to do a limiting reactant problem. Now, you might remember from General Chemistry 1 that in a limiting reactant type problem, you have a reactant that runs out before the other reactant. And when that happens, your reaction stops. So in this case, what we're going to do is we're going to try to make the thiocyanate ion, the SCN minus ion, run out before the iron 3 plus. Okay, and the way we're going to do that is we're going to use a much smaller amount of the SCN at the beginning of our reaction. Now, based on the reaction stoichiometry, this is a 1-to-1 ratio between the SCN and the FeSCN. So the initial amount of thiocyanate is approximately the same as the equilibrium amount of iron thiocyanate. So we can do a quick calculation to find the initial amount of SCN minus, which really comes from KSCN, and that amount will be equal to the amount of iron thiocyanate found at equilibrium. Now, once we have this equilibrium number for the concentration, what we can then do is take this known concentration and put it into a spectrophotometer. Now, you've already used a spectrophotometer in the first semester lab when you were looking at Kool-Aid concentrations and their color. And what you might remember is that at a low concentration, you had a pretty lightly colored solution, but at higher concentrations, your solution got darker. All right, now this is related to something known as the absorbance. So what the spectrophotometer does is it shines light through your solution and it measures how much of that light is actually transmitted through your solution. And the amount that's lost, we just say that that's the absorbance. All right, and Beer's law is sort of this relationship. You might remember that Beer's law says the absorbance is equal to a couple of constants and the concentration. The important thing to recognize is that absorbance and concentration are proportional to one another. So as the concentration of our iron thiocyanate solution increases, the absorbance value should increase as well. All right, so in other words, the darker the solution, the less light that is going to pass through it, and the more light that is going to be absorbed. Now, you might remember also when you were looking at the Kool-Aid lab that you created something called a calibration curve. What a calibration curve does is it looks at the relationship between absorbance and concentration graphically. So in the lab, the very first calculation that you're going to do is you're going to calculate the concentration of your iron thiocyanate. You will be given some absorbance values. Now, normally you would be measuring these in labs yourself, but because you're not on campus, these values have been provided to you. So with those calculated concentrations and the absorbance values given to you, you can create a very similar looking curve to the one shown on this slide for your data. Now, what's important to understand is absorbance is on the y-axis and concentration is on the x-axis. Now, in our case, concentration will have molarity units, not gram per liter units. Once you've got your graph plotted, you can plot out the line of best fit. And what that line of best fit does is it relates absorbance to concentration. Now, if you don't quite remember how to make a plot, I've included a YouTube link here for a creation of a calibration curve. So, a couple of notes about the calibration curve. Number one, the calibration curve is really only good for the data between the lowest absorbance value and the highest absorbance value. So what this means is your curve is not going to be good for all the data that you could theoretically gather, but as long as your absorbance values in the sample that you're looking at falls between your lowest and highest values, then the calibration curve will be able to predict your concentration. So just real quick to remind you how we could use this calibration curve, let's say we go back to the previous slide and we look at the line of best fit. What we have is this equation. Y is equal to 1.0808 times x plus 0.1541. Now what we want to remember is that absorbance on our calibration curve is on the y-axis, and on the x-axis we have our concentration. So what you're going to get in this lab is you're going to get some sample absorbances, and the goal is to use a calibration curve to calculate the concentration of those sample absorbances. So let's just say, using this calibration curve for Kool-Aid, that you were told you have an unknown sample solution that has an absorbance of 0.700. You can plug that in for the spot on which absorbance is plotted on your graph, and that's the y-axis. All right, so if we plug in 0.700 on the y-axis, or the y value in this equation, we can solve for x. Now what's x? X is our concentration. Okay, so we can do the math really quick, and what we find is that x is equal to 0.505. All right, now the concentration unit again, based on this calibration curve for the Kool-Aid, was in grams per liter. Your concentration unit will be different. It will be in molarity. One other note, the line of best fit for your data is not going to be this equation on this slide. This is just an example. All right, so let's say we've now calculated an absorbance of FeSCN using our calibration curve. What that value tells us is the amount of FeSCN at equilibrium. Okay. Now that we have that value at equilibrium, we can use that one single number to calculate the amount of iron 3 plus and thiocyanate at equilibrium as well. All right, and the way we can sort of do this is by creating an ICE table or a RICE table, depending on how your instructor defines it. All right, I'll use RICE here because what really matters is we have this balanced chemical reaction that we're using the stoichiometry from. So just as a reminder, to calculate the values in an ICE table or RICE table, the first thing we need to know is the initial concentrations of all of the components in our reaction. So for your samples 1 through 5, you can calculate both the iron 3 plus and the SCN minus before your reaction begins. All right, so this is going to be the iron 3 plus in your solution at time is equal to 0, and the same for thiocyanate at time is equal to 0. Now, because the reaction is not started yet, the amount of iron thiocyanate at the beginning is also 0. Okay, now, because you are actually given absorbance values that you can plug into your calibration curve, That tells us the amount of iron thiocyanate at equilibrium. Okay, so you have a starting amount of 0 for iron thiocyanate. You have a value at equilibrium for iron thiocyanate. That tells us something about the change in concentration of iron thiocyanate. So we know that the concentration goes up for iron thiocyanate. Now, for the reactants, we know that those decrease over time. Okay, so using the initial values of iron 3 plus in thiocyanate, we can use the change and calculate an equilibrium value. All right, and an example for this is gone through in your lab handout as well. So the idea is you're going to first create a calibration curve using standard solutions A through F. Once you have that calibration curve, you are then going to take absorbance values for samples 1 through 5. Okay, so note we're jumping from letters in our standards to numbers for our samples. You will calculate equilibrium concentrations of iron thiocyanate using the calibration curve, and then iron 3 plus and SCN minus using ICE tables. Now, all of those values at equilibrium can be used to calculate KEQ, or the equilibrium constant. Okay, so the idea is you're going to get 5 equilibrium constant values. Then you can find the average equilibrium constant for this reaction. Okay, so all of this is going to be sort of done step by step for you on an assignment that has been posted in your lab course Mastering Chemistry page. So you are not going to be filling out lab notebook pages any longer. Your assignments will be turned in through Mastering Chemistry by using the data that we provide to you and then doing the calculations that the lab has you do. All right, so that's it for this pre-lab. If you have any questions, please reach out to your instructor.